Hello, today is lecture 14. We discussed test of homogeneity, test of independence, and then some practice. Now today was a day when a lot of you decided to go to the beach, which I really can't blame you because it was a beautiful day in Berkeley, but I'm glad we have these videos to help you get back on track. So here we go, test of homogeneity. So this is a test whether two or more multinomial distributions are equal. And to best illustrate this, we'll look at a problem in the book, problem 1 actually, in chapter 13.8. So a study was done comparing the frequencies of a particular allele in a sample of diabetics and non-diabetics. The following data table is observed, and you can see that in the rows you have diabetics and not diabetics, and in the columns you have various allele types. And the question is, are the relative frequencies of the alleles significantly different in the two groups? So what this is really asking is, are these two circled groups here, are the distributions in these circles here the same, or are they significantly different? So that's a tough question here as you look at it. They look kind of similar in that the dominant allele here, capital B, is highest frequency, but there are differences in the numbers. So this is the question that we want to ask. Our null hypothesis is that the multinomial distributions are the same, and the alternative is that they're different. So I tried as best as I could to keep with the book's notation. This is a little bit strange, but we'll roll with it. So our box here, we actually have two boxes, a box for diabetics and a box for non-diabetics, but the null hypothesis is that the distribution in those boxes are the same. So I'm just going to write them as a single box, and I'm putting the box on its side like this because the distribution has, in this case, two cells, more generally I cells, and the number of multinomials we're testing is, in this case, 2, but more generally J, and J comes after I in the alphabet, and so we would want I to be rows. So I'm writing the multinomial distribution like two different rows here, pi1 and pi2. So that's why it's kind of on its side like this, because I generally is going to be the number of cells in a multinomial distribution running down, and we're going to have J multinomial distributions along the columns. Okay, so I've written it as a single box, but it's really two boxes here, and I draw 51 diabetics and 53 non-diabetics. I can tell it's 51 and 53 because of these numbers here in the margins, and then I get this observed table that I was presented before, and I've just written the marginal frequencies here. And now we want to write out the expected table. And so what is that? So for the first cell here, what it should be is we have 51 diabetics times pi1 is a probability of being allele type BB or BB. So it should be 51 pi1 here, except that we don't know what pi1 is, so we have to estimate it. And how would we estimate it? Well, so the probability that we're BB or BB, there's 16 of those out of 104. So that's our estimate for that probability. And we're going to do something very similar for all of these cells. And then we need to come to what the dimension of the chi-squared is going to be. Now the dimension is omega minus dimension of omega naught. Omega naught is the dimension of the null space, and we essentially have we have a single null box, right? We have a single null box, and so we have this one multinomial here. In this case, there are two probabilities here, which add up to 1. So there's really one free probability. So I'd say the dimension of omega naught would be 1. But more generally, if we have a multinomial with I cells, then I minus 1 would be free. So we'd have dimension I minus 1. Now, we have J. Let me see, make sure I'm doing things right. I said it right. So now we come to capital Omega. So capital Omega, this is the alternative and the null space. So more generally, we have J of these multinomials. Each multinomial has I cells. So we have I minus 1 free cells per multinomial, J multinomial. So that's J times I minus 1. I'm so good today. Now the degrees of freedom then would be J times I minus 1 minus I minus 1, which is I minus 1 times J minus 1. I can even do algebra. So for our example, that is 2 minus 1 times 2 minus 1 is 1. So we can calculate then our chi-squared with 1 degree of freedom. We do some rocket science here, and we get 5.15, and we can compute the p-value for that if we wanted, and see that it's 0.023, which is less than our alpha 0.05, so we reject the null. The relative frequencies of diabetics and non-diabetics is significantly different. I knew that anyway. If you wanted to do this in R really snazzy, you need to convert the vector 12, 4, 39, and 49 here, your observed values, into a matrix. Tell R that there are 2 rows and that you're adding the numbers by row, and you can check that the matrix you get is what you think it is by just writing A in the console. And then you can do a chi-square test using the most awesome R command ever, chi-square.test. So you just enter A, which is the name of your matrix, and then correct equals false. Correct is that you don't want a continuity correction, because we are friends, right? So we get 5.10 with 1 degree of freedom and a p-value of 0.024. It is so awesome. I just want you to notice that if instead of A you enter T of A, which is the transpose of A, you get exactly the same output. And as we'll see below, this is because if you flip your I's and your J's, it doesn't make a difference for this test. So then we went through the theory, and this is where it really gets fun. Everyone woke up for this part. So here we have J independent I cell multinomials. Did you get that? And H0 is that all J multinomials are the same, and the alternative is that they're not all the same. And so here's a picture similar to the picture we had before, but now we have j is 3. So our observed is now a 2 by 3 table. And following the notation of the book, I denote n.1 to be the number of draws from the first box, n.2 the number of draws from the second box, and n.3 the number of draws from the third box. I fill out my table here, and the column and row marginal frequencies are as given here. And in just an absolute brilliance, the total sum is denoted by n dot dot. So the expected counts are what's shown here, and I'm just not going to say anything about this because it is just so beautiful that no words that I can conjure will give it justice. So the TS then was given here, and this formula here is the general formula for the TS. And if you stare at it long enough, you'll realize that this is symmetric in I and J, and so that is why if you flip I and J, you get the same TS.